Good evening to everyone. So today we are going to discuss about time averages of a random process. So in this time averages of random process, first of all, we are going to know what is meant by a time average function, followed by time autocorrelation function and its properties, as well as time cross correlation function and its properties. So this is going to be our today's session, right? So in order to understand the time average function of a random process, first of all, let us consider a random process capital X of t and its sample function is small x of t. And this sample function is going to be exist for all time at fixed samples, right? And now the basic definition of the time average function is that the average value of the sample x of t taken over all times is called the time average of the x of t, right? And it is also called as the mean value of x of t, and it is given by a mathematical formula. Just wait, I will show you this the mathematical formula. Okay, just wait. So see, this is the mathematical formula of a time average function. Right, all of you observe here carefully. So this is the mathematical formula of time average function. So see, there is x bar is there and a into x of t, which is also going to equal with the limit t tends to infinity 1 by 2 pi integral minus g to capital T into x of t dt. So this is nothing but the mathematical representation of the time average function. I am repeating once again the basic definition of a time average function. That is, the average value of the sample x of t taken over all times is called time average, and it is represented like this. That is x of t. Time average, right? This is the formula. Next, we would like to discuss about autocorrelation function. So as we know previously that what is the meaning of autocorrelation function, but today we are going to see what is the difference between time autocorrelation and correlation. General autocorrelation, that is, right? So here the time autocorrelation function is nothing but the time average of x of t and x of t plus tau is called time autocorrelation function of a random process x of t, and it is also represented by the formula. So observe here. So this is nothing but the formula to calculate time autocorrelation function. That is, if you are going to observe if it is autocorrelation, then we have to represent both these letters are same. Observe here, Here x is there and here x is there. Right? So this is nothing but a time average. So in order to represent this function is a time function, we are going to use this notation, that is A. Right? And see here there is x of t and there is x of t plus tau. And the formula to calculate RYY, right? You see, that is equals to limit t tends to infinity 1 by 2 pi integral minus t to t x of t into x of t plus tau. So observe here, there is capital X of t and there is capital T plus tau is there. But here we have only small x of t and small x of t plus tau. So this is nothing but random process and this is nothing but a sample function, right? So these are the two equations for time autocorrelation function. So remember these two equations in a proper manner. So these are very helpful in our future in order to solve some problems. So in the equation of autocorrelation function, we had observed the tau. So this tau is nothing but a time difference value. So now we would like to move to know about what is time mean square function, right? Time mean square function is nothing but if the time difference value, that is tau equal to 0, and the time average of x square of t. So see here, the time average of x square of t is called the time mean square value of the random process x of t, right? And it is given by the mathematical formula, that is a into x square of t, that is equals to limit t tends to infinity 1 by 2 pi integral minus t to t x square of t dt. So this is the basic formula to calculate the time mean square value of a random process x of t. And now we would like to see the properties of time autocorrelation function, right? So there are 9 properties are there. This is the property 1 for this autocorrelation function. So that is the mean square value of x of t is expected value of x square of t is equal to rxx of 0, right? And it is equal to the power of the random process x of t. And all of you observe the proof here for the random process x of t. For the random process x of t, here rxx of tau is equal to expected value of x of t into x of t plus tau. And for example, if tau equal to 0, then we are going to put in place of tau here 0, then it is going to be becomes look like this, that is e of x of t into x of t, that is equal to e of x square of t. Hence this property is proved, right? So this is about the property 2, and now we would like to move to property 2. So the property 2 is going to tell us the autocorrelation function is maximum at origin. That is, mod rxx of tau is less than or equal to rxx of 0, right? So in order to prove this property, here we are considering two random variables, that is x of t1 and x of t2 of a random process x of t defined at time intervals t1 and t2, right? So here our random process is x of t, and here we are considering our random process at two different time values, that is t1 and t2, and our random variables are x of t1, this is the first one, and x of t2, this is the second one, right? So if you consider a positive quality, then it is going to represented by the following function, that is x of t1 plus or minus x of t2 whole square greater than or equal to 0, right? And take the expected value of this one, that is e of x of t1 plus or minus x of t2 whole square greater than or equal to 0, right? So, and expand this by using a plus b whole square formula. Internally, the equation will be look like this, right? So that is x square of t1 plus x square of t2 plus or minus 2 into x of t1 into x of t2, that is greater than or equal to 0. And by the property of mean, that is e of ax equal to a into e of x. Now we are going to expand this function like this. Take individual expected values. That is for x square of t, we are going to write like this. And for this x square of t2, we are going to write like this. And here we are going to use this relation, that is e of ax is equal to a into e of x, which is also greater than or equal to 0, right? And if you substitute e of x square of t is equal to rx of 0, now we will see what happens if you substitute this relation, that is x square of e of x square of t is equal to 0. So see, if you substitute this expected value of x square of t is equal to rxx of 0 in the above equation, then we are going to get rxx of 0 in place of expected value of x square of t1 and in place of expected value of x square of t2 also. But here we are going to rewrite the same one. So in the equation we have e of x of t1 into t2, that is represented like this, rxx of t1 comma t2. So this representation rxx is going to indicate as the autocorrelation function, and here we are discussing the autocorrelation function in time factor. That's why this is called as time autocorrelation function, right? And we know that if the given random process is a wide sense stationary process, right? So for the consideration of wide sense stationary process, that is the tau is nothing but the time differences, that is tau equal to t2 minus t1, t2 minus t1, and if you add here rxx of 0 and rxx of 0, we are going to get 2 rxx of 0, and this is nothing but here we have the time instance, that is t1 and t2, and by modeling this equation or by considering here this autocorrelation function is going to be treated as a time difference function, then we are going to replace this t1 and t2 time instance with this tau, right? So 2 into Rxx of 0 plus or minus 2 into Rxx of 0. So if you are take the 2 as a common value from this and from this and move on to RHS 0 by anything is 0. That's why here we are going to get this value Rxx of 0 into Rxx of tau, which is greater than or equal to 0, right? So if you maintain this equation, by simplifying this equation, we are going to get Rxx of 0 greater than or equal to Rxx of tau, right? But here, this is the another way of representation. Hence, the statement is proved. That is, mod Rxx of tau is less than or equal to Rxx of 0. So if Rxx of tau is less than or equal to Rxx of 0, then the statement is also valid, right? So as far as considering this second property, the autocorrelation function at the origin. So here the autocorrelation function at origin is going to be represented with Rxx of 0, and it has the maximum value, right? And here this Rxx of tau is bounded by its value at origin. So what is the bounded value here? It is going to depends on the time differences. That is T2 minus T1. Here, observe here. This is bounded to these two instances only, right? Hence, the property 2 is proved. Then we are moving to the third property. That is, in the third property, the autocorrelation function Rxx of tau is an even function of tau, right? The Rxx of tau is an even function of tau. That is, if you are placing a negative sign in the autocorrelation function, that is Rxx of minus tau is also going to give us the same value. That is Rxx of tau. Just wait, I will show you with a mathematical proof. So see here. So this is Rxx of minus tau, and this is Rxx of tau. So for placing negative sign here, we are getting the positive sign here. So this is nothing but the tau is an even function. And for the proof of this above statement, that is for this statement, here we are going to consider Rxx of tau is expected value of x of t and x of t plus tau. And if you put tau equal to minus tau here, then Rxx of minus tau is equal to E of x of t into here. Look at here. In this place, we are going to substitute the relation. That is tau equal to minus tau. Then it will be look like this. That is x of t minus tau. And now we are making one more consideration, that is mu equal to t minus tau, right? Then this equation will be look like this. Rxx of minus tau is equal to expected value of x of mu plus tau. See here, if you rewrite this one by using this equation, here we have the relation, right? And if you want to know this x of t value, so this is nothing but x of t and this is nothing but x of t minus tau. So simply here the t minus tau value is going to replace with this consideration. That's why here we are going to represent this x of u. And if you simplify this one, you are going to get the t value. That is, if you move this tau towards mu and make it t on RHS, then you are going to get x of mu plus tau, right? So here, see, Rx of tau is equal to expected value of x of u into x of u plus tau. Or simply, we are going to treat this one as Rx of tau is nothing but Rx of tau. So we had started with a negative function, but finally here we are going to get a positive function. So this is about the third property, and now we would like to move to the fourth property. So the statement of the fourth property is, if a random process x of t has non-zero mean value, okay, that is, the expected value of x of t is not equal to 0 and ergodic with no periodic components, then limit mod tau tends to infinity Rxx of tau is equal to x square bar. Just wait, I will show you the mathematical representation and proof. Okay, see, so this is the statement, that is limit tau tends to infinity Rxx of tau equal to x square of bar, right? So in order to prove this property, we are going to consider a random process x of t with random variables x of t1 and x of t2. And if the mean value is given as, that is non-zero mean value. So if it is a non-zero mean value, then we are going to represent like this. That is, the expected value of x of t is equal to x bar, which is not is equal to 0. And this is the basic formula of autocorrelation function. And we know that this tau is the function of time differentials. That is, expected value of x of t into x of t plus tau is the formula. And if you replace this with two random variables, that is x of t1 and x of t2, then it will be look like this. That is expected value of x of t1 into x of t2. And we know in the statement here there is no periodic component is there. Okay. And here the tau is going to tend towards infinity. Then the random variables become independent. So here, this is nothing but the independent, right? We are going to write these two as individual. That is expected value of x of t1 and expected value of x of t2. So see here, there is something missing here. That is, I think, mod tau tends to infinity. Rxx of tau is equal to expected value of x of t1 into expected value of x of t2, right? So here, if x of t, that is our random process, is an ergodic, then we are going to represent like this. This is e of x of t and this is e of x of 2. That is equal to x bar, right? And finally, simply using this equation, if it is x bar and this is also x bar, we know by the basic function, that is expected value is represented with x bar. So here we have x bar and here we have x bar. So x bar is multiplied with the x bar, then we are going to get this one, that is x square whole bar. Hence the property is moved, but we have to know what is ergodic here. And here our random process is ergodic, and we have to know the basic meaning of ergodic. So here ergodic is nothing but all the time averages of a sample function x of t are equal to the corresponding ensemble or statistical averages of x of t, then it is going to treated as ergodic. So don't worry about this ergodic definition. If it is very clear to you or not, we have the upcoming concept, that is ergodicity. While we are discussing about the ergodicity, we are going to know in detail, right? So next we are moving to the fifth property, that is if x of t has a periodic component. This is the statement of the fifth property. If x of t has a periodic component, then its autocorrelation function is also periodic, right? Just wait, I will show you the proof for this fifth property. So see, if x of t is a random process and we know that it has a periodic component, then observe here, Rxx of tau plus t naught is equal to Rxx of tau. So if the random process x of t is also periodic, then the autocorrelation of this random process is also periodic, right? So here we are considering the same consideration, that is a random process x of t is periodic with period t naught. Then we are going to consider like this, x of t is equal to capital X of t plus or minus t naught, or x of t plus tau is equal to x of t plus tau plus or minus t naught. But we know that by the basic definition of autocorrelation function, that is Rxx of tau is equal to E of x of t into x of t plus tau. Then here we are going to represent like this, that is Rxx of tau plus t naught is equal to x of t into x of t plus, see, if you have only tau here, here we are going to represent with only tau. But here we have tau plus or minus t naught. That's why here, look at in this equation. Here we have only tau. For tau here, here also we have tau. So here we have tau plus or minus t naught. That's why here we are replacing this one, right? And if x of t is a wide sense stationary process, right? Then we are going to treat this one, that is Rxx of tau plus t naught is equal to E of x of t into x of t plus tau. We know the basic definition of a wide sense stationary process. This is not going to vary with the time. So that's why here we are not going to bother about this time constraint. That's why simply we are rewriting this function like this, that is Rxx of tau, right? So this is about the fifth property, and now we would like to move to the sixth property. So what is the statement of sixth property here? If x of t is ergodic and it has zero mean and has no periodic component, then limit mod tau tends to infinity Rxx of tau is zero. So just wait, again I would like to show you the mathematical difference. So see here, So this is our statement, that is limit mod tau tends to infinity Rx of tau equal to 0, right? And see from the fourth property. So that is limit mod tau tends to infinity Rx of tau is equal to x square of bar. So this is represented here, right? And x bar is a mean value of x of t. And here the mean value of x of t, that is equal to 0. That is x bar is equal to 0. Then it is valid. That is limit mod tau tends to infinity Rx of tau is equal to 0. Next, we would like to move to the property 7. Property 7 is a theoretical one. That is the autocorrelation function of a random process Rx of tau cannot have any arbitrary shape, right? So in order to prove this one, we are going to consider the autocorrelation function Rx of tau is an even function of tau and have maximum value at origin, right? And this autocorrelation function is related to the power density spectrum through the Fourier transform, and the form of spectrum is not arbitrary, so the autocorrelation function cannot have an arbitrary shape. So there is no mathematical relations to prove this property 7, but we have only theoretical assumptions based on this power density spectrum, that is simply Fourier transform, and here we have no arbitrary shapes in this Fourier transform. So now we are moving towards the property 8. Just wait, I will show you the 8th property statement as well as proof. So see here, if a random process x of t with 0 mean has a DC component A, then we have y of t is equal to a into x of t, then ryy of tau is equal to a square plus rxx of tau, right? So what is the random process here we are considering? Y of t. So y of t is equal to a into x of t, and we know that by the basic definition of autocorrelation function, ryy of tau is equal to e of y of t into y of t plus tau, right? So here we are representing the function in place of y, a plus x of t into a plus x of t plus tau, because here we have t plus tau, right? If you multiply both these terms, that is a of x of t into a of x plus, a plus x of t plus tau, then we are going to get this simplified value. And observe here e of x of t is there, and a into e of x plus, so x of t plus tau is there, and here also this is going to be treated as rxx of tau, So this is the substitution here. We know that it has 0 mean, so here we are replacing with 0, a into 0. Here in this term also a into 0, and this is nothing but a autocorrelation function of x. That is, we are going to prove this one. Here, this is the statement. Ryy of tau equal to x square plus rxx of tau, which is proved here by considering this one. So next, we would like to move to the last property of the autocorrelation function, that is property 9. So see here. So this is the statement of the ninth property. And here we are considering the random process as z of t. And this z of t is nothing but the summation of x of t and y of t. Then the autocorrelation function of z is nothing but the summation of rxx of tau, rxy of tau. This is nothing but the cross in between x and y. That's why this is called as cross correlation function of x and y. And this is the cross correlation function between y and x. And this is nothing but autocorrelation function of y. So z of t equal to x of t into y of t. Then the autocorrelation function of z. As we know that the basic formula, that is expected value of z of t into z of t plus tau, right? So then we are going to get this type of substitution, and by simplifying this one, we are going to get this one, right? And that is e of x of t into x of t plus tau. That is nothing but the autocorrelation function of Rx. So x of t into y plus y of t plus tau. Then it is nothing but a cross correlation in between x and y. So observe here y of t into x of t plus tau. This is nothing but cross correlation of y and x. And this is the direct one, y of t into y of t plus tau. That is y of tau. Hence the statement is true. Here we have started with this z of t function, and we have written the basic definition of autocorrelation function of z, and by simplifying these ones we are going to get here, right? So this is about autocorrelation function, and now we would like to move to cross correlation function properties. Cross correlation function properties. So see, consider two random processes, x of t and y of t. If they are at least jointly wide sense stationary, then the cross correlation function of x and y is going to represented by rxy of t plus tau is a function of time difference. That is tau equal to t2 minus t1, which is very similar to the one which we had seen for autocorrelation. But here we are going to see, first of all, what is the basic difference between rxx of tau and rxy of tau. That is autocorrelation and cross correlation. Just wait, I will show you the properties one by one. So this is the first property, and this is the first statement of this cross correlation function. So before going to discuss about the properties of cross correlation, we would like to know the basic difference of cross correlation and autocorrelation. So see here, this is nothing but the cross correlation representation of x and y, right? So see, if it is rxx, that is autocorrelation, in this first term and in this second term, we are going to observe only one thing. That is, if it is rxx, then expected value of x of t into expected value, e of x of t into x of t plus tau, right? So see here, for this x, we have x of t here, and for this y, we have t plus tau here. So this is the difference between cross correlation and autocorrelation. So in order to prove this symmetry, we are going to follow the proof of x of t and y of t. So here x of t and y of t are wide sense stationary, and we know that the conditions for wide sense stationary, right? So see here, for this ryx of tau, for y consideration y of t, for x consideration x of t plus t. By replacing the tau value with minus tau, then we are going to get like this. And we have to consider similar as like in our autocorrelation function, that is mu equal to u equal to t minus tau, and we are going to get this one, and here this is the t value. Hence the property is proved, right? And we would like to move to the second property. Just wait, I will show you the mathematical representation of the second property. So see, if rxy of tau and rxy of tau are the autocorrelation functions of x of t and y of t, then mod rxy of tau is equal to or less than root of rxx of 0 into ryy of 0. So in order to prove this one, we are going to consider here two random processes x of t and y of t with the autocorrelation functions rxx of tau and ryy of tau. Right? Consider the following inequality, that is e of x of t by root of rxx of 0 plus or minus equal to y of t plus tau by root of ryy of 0 is greater than or equal to 0. Right? By simplifying this, we are going to get our proof. Just wait, I will show. So in another way, we are going to consider like this. So this is for x and this is for y. And this is combination of x and y. So we know that expected value of x square of t is equal to rx of 0, and we have y square t plus tau is equal to ry of 0, and e of x of t into x of t plus tau is equal to rxy of tau. So by replacing these values, by using these relations, we are going to get this one. And there is something missing here, that is nothing but this one, rxx of 0 and ry of 0 greater than or equal to 0. So if you simplify this one, we are going to get the required statement, that is mod rxy of tau less than or equal to root of rxx of 0 into ryy of 0. So this is nothing but the second property, and now we are moving to the third property. So see here, if x of t and y of t are two random processes with autocorrelation functions, rxx of tau and ryy of tau, this is nothing but the same conservation. And this mod rxy, this is nothing but a cross correlation in between x and y, is less than or equal to 1 by 2 rxx of 0 plus ryy of 0. Right? So this we have to prove here. So before going to prove this one, we have to remember 2 points here. The geometric mean of two positive numbers cannot exceed their arithmetic mean. So this is the first point we have to remember here. In the second point, the absolute value of the cross correlation function is always less than or equal to the geometric mean of the autocorrelation functions of x of t and y of t at tau equal to 0. So see, we have to remember these 2 points. Let it be node point 1 and node point 2. So that is the node point 1 is nothing but geometric mean of two positive numbers cannot exceed their arithmetic mean. In the second one, that is regarding with the absolute value of the cross correlation function. So say if Rx of tau and Ry tau are two positive quantities, then at tau equal to 0, root of Rx of 0 into Ryy of 0 less than or equal to 1 by 2 into Rx of 0 plus Ryy of 0. So here equation 2 is nothing but the property 2, which we know that mod Rxy of tau is less than or equal to root of Rx of 0 into Ry of 0. Okay? So that is here we are going to replace by using that relation like this. Mod Rxy of tau less than or equal to 1 by 2 into Rx of 0 plus Ryy of 0. Right? So this is nothing but the third property, and now we are moving to the fourth property. Just wait, I will show you the statement and proof of the fourth property. So see, if two random process x of t and y of t are statistically independent and they are wide sense stationary process, then Rxy of tau is equal to x bar into y bar. So in order to prove this one, we are considering here the basic formula of cross correlation. That is, here the cross correlation function in between x and y. So that's why here we are represented like this: expected value of x of t and y of t plus tau. If x of t and y of t are independent, then we are going to write like this, right? So this is nothing but x bar, this is nothing but y bar. So this is regarding the fourth property, and now we would like to move to our last property, and maybe this is the last point that we are going to discuss in this session. Just wait, I will show you. So see here, if two random process x of t and y of t have zero mean and jointly wide sense stationary. So we know that the conditions for wide sense stationary already that is discussed in our previous class. So this is the statement of the fifth property, that is limit at tau tends to infinity, the cross correlation function is equal to 0. And here also we are considering two random process x of t and y of t, and this is nothing but the basic definition of cross correlation function in between x and y. So taking limits on both sides for this equation, it will be look like this. As tau tends to infinity, the random process x of t and y of t can be considered as independent process. So we are rewriting like this: e of x of t into e of y plus, e of y of t plus tau. So this is going to be treated as x bar, and this is going to be treated as y bar. So x bar equal to y bar equal to 0. Then the RHS is going to become as 0. The entire RHS is going to become 0. So therefore, limit tau tends to infinity, Rxy of tau is equal to 0. Hence, it is proved. The statement is proved. Right? So this is today's session. If you have any doubts, ask me in the comments. Right? Thank you. Have a nice day.